Hello everyone. Today's presentation will be concerning Stayalives circuits for locomotives and coaches. I'd like to thank Davey for enabling me to use material from a presentation that he provided some time ago. Let's look at the problem that requires the Stayalives circuits. We have locomotives that do not run smoothly at slow speed. We have locomotives that may just stop completely, or we have coach lights or running lights that just may flicker, and we have sound decoder problems, which results in endless cleaning of track and wheels. Let's look at why this occurs. Some of the reasons for poor running include dirty track, which is self-evident, dirty wheels, which are often overlooked, old motors, such as the Ringfield and XO3, XO4 motors that we see here in the images, uneven track, and insill frogs, which are the points which can often cause a problem, especially to short wheelbase locomotives. Limited pickups, especially on older models, can, of course, cause a problem with connectivity with the rails. If we look at a wheel in close detail, it becomes more obvious why this is a problem. Each wheel has a minimal contact with the rail, and not every wheel has a pickup. So if there's any problem with the track, then we lose connectivity. The solution? Some form of power storage or Stayalives. This takes the form of energy stored inside either the locomotive or the coach. During the track glitches, this energy keeps the locos running, keeps the coach lights from flickering, and prevents any sound decoder stutter. We can go for either a commercial or a DIY solution. Well, let's look at what we need. We need to provide power. We need to regulate the voltage of that power. And we need to maintain that voltage for sufficient time for the wheels to once again run along clean track. Stayalives circuits is the generic term that we use for circuits that will provide a solution to this problem. There is a disclaimer, and that is DIY solutions may invalidate warranty on DCC decoders. So think carefully before you decide on a DIY solution. Here's a basic Stayalives circuit. We have the capacitor, which acts as a small rechargeable battery. We have a resistor, and this limits the inrush of current, which may be seen as a short circuit by the DCC controller and would therefore trip it. The diode acts as a low resistance discharge path. In this case, the capacitor is 2200 microfarads, the resistor 100 ohms, the diode is a 1N5819 Schottky, but in practice, the standard 1N4001s would be quite acceptable. Here we have an example, albeit an extreme example, of a Stayalives working. The small diesel clearly does not have a Stayalives circuit. let me provide a few words of caution. Stayalives are not intended as a substitute for track and loco maintenance. Use realistic values of capacitance to achieve approximately a half to 1 second power storage. And the reason is that excessive stay-alive times can result in locomotives overrunning totties, signals, etc., as the decoder cannot receive signals from defective track. Stay-alive time depends on the motor. Low current motors will run longer per unit charge than typically older, more current hungry motors. Here we have a simple Stayalive kit. Various capacitors from 1000 up to 4700 microfarad. But notice the dimensions of the capacitor, which is the large electrolytic. They increase with capacitance. And you may find that some of the larger values become difficult to fit into confined spaces. Also note that the actual cost of an electrolytic capacitor, let's say the 4700, a resistor, a diode, probably come to no more than 50 pence. So you don't have to buy a commercial kit. Let's look a little more closely at capacitor values. Here we have a typical electrolytic cap. You see the negative lead, which is always marked by a stripe, the minus sign. Value is clearly marked, in this case 4700 microfarads. And pay attention to the working voltage. In this case, 16 volts. This is the maximum continuous working voltage that is safe to use this capacitor at, above which you run the risk of damaging it. DCC controllers normally output a DC voltage of approximately 12 to 15 volts after rectification. The capacitor voltage rating must therefore be greater than the expected DC output voltage. The physical size also increases with voltage rating as well as the value of capacitance. In this instance, a 16 volt version measures about 16 by 31 mil, but go up to 25 volts working voltage, and we're looking at 18 by 35. So again, you have to ensure that you have space to accommodate these larger values. Most commercial Stayalives use a 16 volt rated capacitor, but check your controller specification. Let's look at Stayalives for DC locomotives. Now, unfortunately, electrical Stayalives are not well suited to DC locomotives. The required capacitance, both electrical and physical, would need to be large to make any significant difference. DC controllers, unlike DCC controllers, do not provide a constant voltage to charge the capacitors. And while in typical operation, the voltage is typically about half maximum, let's say about 6.5 volts. However, there is an alternative. There is the flywheel Stayalive for DC locomotives. The flywheels are quite common on N scale and smaller scales. They provide smoother running by using the stored mechanical energy or kinetic energy generated by the flywheel. And here you see a couple of examples. There are some double-O scale locomotives, such as Hornby, who use flywheels, but space must be available to fit them. And here you can see a typical Hornby mode with the flywheel, brass flywheel, on the end of the motor shaft. Let us now look at Stayalives for DCC decoders. There are commercially available Stayalives circuits for most of the main DCC decoder companies. Current Keeper for soundtracks, Keep Alive, TCS, No Halt, NCE, Power Extender, Digitrax, Energy Store, Zemo, USP for lens. But how do we connect a Stayalive? Here we have a schematic of a simple 4-function decoder, non-sound. The color-coded wiring is standard. And you'll see here that we have black to the left rail, red to the right rail, orange and gray to the motor, and blue is the common positive. Remember that, we will come back to it. So where do we connect the Stayalive? Well, if we look at a generic DCC decoder connection, we will see that they all have a blue common positive and a ground. We need to identify those and attach the Stayalive accordingly. The positive side of the Stayalive will go to the common positive, the negative to the ground. Here's a typical example. This is a Zemo 632, one of their older decoders, and again it's a non-sound, fairly basic decoder. However, it does provide two specific pads, here marked blue and gray, to attach a Stayalive capacitor to. This decoder just requires a capacitor to be added to the blue and gray pads, but not all decoders have the additional components, i.e. the diode and resistor, and therefore a separate circuit is required. Again, check the decoder manual for details. Here's an opportunity to add a Stayalive unit to any decoder. The LifeLink circuit is a small PCB that you can attach your own capacitors to. It's also available from BuChoose with various combinations of tantalum capacitors, which are another form of electrolytic. Also at the bottom of the list, you'll see the term supercap or supercapacitor. You'll see that the capacitance has increased dramatically. We have two options there, 6,800 microfarads and 17,000 microfarads in a relatively small package. We'll be covering supercaps in detail in a few moments. But notice, of course, the cost associated with the various options. Here is a Hornby TTS sound decoder, and it does not have any specific pads to add a Stayalive to. It is still possible to add a Stayalive circuit, but it would most definitely invalidate the warranty because it requires soldering to the two pads indicated, which are the positive and negative terminals of the bridge rectifier. I would caution that this takes very fine soldering, as we're talking about maybe 0.5 millimeter to 1 millimeter of the pad size that you'd have to solder to. Similarly, the lens silver offers the opportunity to solder connections to the ground, and of course the positive goes to the blue. Coming back to the supercapacitors. Supercapacitors can hold a charge of between 10 and 100 times that of similar size electrolytics, but at a lower voltage, which makes them ideal for model railway applications. And here we have three possibilities, again from U-Choose: a 6800, a 17,000, and a whopping 120 millifarad capacitor. So you can see from the physical sizes at 20 by 15.5 by 8, they are relatively small and should fit in most applications. Costs are accordingly 14, 22, and 55 pounds respectively. They're not cheap, but they do a great job. Let's look at the DCC decoder Stayalives summary. Stayalives will improve the running of most DCC locomotives. Check the decoder manual for Stayalives suitability. Check the decoder manual for Stayalives connections. Stayalive time is highly dependent on the type of motor in your loco. Supercaps provide the highest charge in the smallest package, but also the highest cost. Beware of decoder warranty conditions. Now let's have a look at Stayalives for coach lighting. But before we cover the Stayalives, we need to look in more detail at coach lighting itself. Coach lighting adds an extra dimension with ready-to-run coaches readily available from all of the main companies. However, the PMP-19 automatic coach lighting kit can be modified to run directly from a DCC track. A Stayalives circuit can be added to this to prevent light flicker due to poor electrical contact. Let's see how it looks. Here's another disclaimer. The following kits do require modification, drilling of the coaches, so please practice on scrap coaches until you're satisfied that you have developed sufficient skill to modify more expensive coaches. You have been warned. This is the PMP Kit 19, automatic coach lighting, and if you want the full details, then go to the June 2015 journal. This is an extract from the article, and you'll also find it in the kit information. The pros, at £2.42 for the web price, it is a bargain. It's not vibration sensitive, unlike many of the commercial examples, suitable for DC and DCC. And you can customize the LEDs and the positions to suit your own coaches. It has an external battery, so if it needs to be replaced, you do not have to take the coach apart. But looking at the cons, it does require switching off after use to preserve the battery life, and installation requires coach modification. So let's look at how do we convert the DC version to DCC. The full article is in the December journal 2018. Let's look at a few details. The pros are it takes power from the track. No batteries, it automatically functions when the track is powered. The cons, it is DCC only. and a DCC to DC converter is required. Pickups are also required. Here's a schematic of the DCC to DC converter, and from left to right we have the track pickups, which we'll cover in a moment. We have the bridge rectifier, the main electrolytic cap, voltage regulator, 3.3 volts, decoupling cap, and here we have the coach lighting module, which will be powered from 3.3 volts DC. Here we have pickups, in this case axle springs. There are a number of ways of taking power from the track, but the axle spring provides a virtually friction-free contact versus the drag that you will get from metal strips that you will typically find on commercial units. One wheel must be live to the axle for this to work, of course. And the DCC concepts, axle springs and axle sets are recommended. The axle springs cost roughly about 35p each in packs, and the axle sets approximately £2 each. They're available in OO, HO, and EM. The advantage of the axle sets is that they come complete, and all you need to do is make the connection. The axle springs require additional work. A more recent innovation, also from DCC Concepts, are these wipers. They have gold-plated pickups. They're easily attached to coach bogies, and no modification is required to the wheel sets. In addition, they can be added to loco tenders to significantly improve power pickup. So this would also be a great benefit to those who operate DC. If your loco tenders are not already provided with power pickups, then this is an ideal way to do it. 12 for $16.95 from DCC Concepts. So this is how they are attached. You can see in the top diagram, the wipers are either screwed or glued between the wheel sets, and you can see the gold contacts making contact with the inside of the loco wheels. The reason that wipers have only been added to the outer sets of axles is that on these tenders, the inner axles tend to float, and therefore they do not make great contact with the track. You'll also notice on the right-hand side that the wipers are connected to the loco via JST or similar micro connectors. More of that in a moment. Here are typical JST connectors. They vary in pin size, and they also vary in physical size. The ones that I've been using are ZH, or 1.5 millimeter pitch. Most pre-wired connectors, however, use greater than 32 AWG wire. This is thick enough that it can cause derailments. I'd recommend that you use 32 AWG, which is decoder wire. However, you may find it difficult to obtain pre-wired connectors, and therefore you may have to scratch build using JST crimps, plugs and sockets, but this is fine work due to the fine size of the ZH connectors, and in addition you'll need to invest in specialized crimp tools. All of this has been covered in an excellent recent presentation by Chick, so I don't intend to go into any more detail on this one. Here is one of the exhibition coaches that we use. In this case, it's an LMS third brake. It was chosen specifically because there is plenty of room in what would be the guard's van to house the Stripboard version of the PMP 19 kit and the additional board required for the DC to DCC connector. And subsequently, as you'll see, the Stayalives circuit. It works very well, but it does take up a great deal of space, and it requires modification to the coach. If we look at the LMS Composite Coach, it's even worse. There's minimal space to locate the lighting circuit and the DCC converter. And here on the left-hand side, you'll see a stripped down version of the lighting circuit, and an internal wall has had to be taken out of the coach to shoehorn it in. Here it is. And on the right-hand side, you'll see the DCC converter. So this really is a tight fit for a 00 coach. In December 2018, Fraser Smith designed a PCB version of the PMP 19 kit. DCC to DC converter is built in, and you'll see that the lower section here comprises of the bridge rectifier, in this case 2 packages, each containing 2 diodes. We have the main electrolytic capacitor and the ancillary resistors and small caps. Here is the 3.3 volt voltage regulator, and here is the PIC. As you'll see, they're all surface mount components. It's not available as a kit, but black PCBs can be ordered through Fraser, but the minimum quantity is around about 120. If we look at a comparison of the Stripboard versus the PCB version, at first glance, it would not seem that there is a great space saving, albeit the image on the left does not contain the Stripboard version of the DCC converter. When you look at the image on the right, you can see where the space saving is. It's in the profile of the PCB. This allows us to install it into a coach quite easily in the roof space. And you can see the PCB in the center with the wiring going out to the LEDs held in small strip of plastic. And on the right-hand side, you can just make out the Stayalive, which we'll come to shortly. Pickup installation is required, of course, and here we see pickup springs being used and heading through the central boss of the bogie and into the body of the coach. Just out of interest, that object on the left-hand side with the blue and black, or what appear to be LEDs, that is the TCRT 5000 and is the infrared transmitter receiver used in the kit, both the DC and the DCC version. Ready-made wheel sets are available, as I pointed out earlier. Adding the springs is much cheaper, but it does require more skill. Let's look at the LEDs, another choice we have. Warm white for period coaches, cool white for modern coaches. 3-volt LED strips are very useful, but they come in fixed positions, which are okay for modern coaches, but not for period coaches. The maximum current that a PIC can supply is 25 milliamps. So we must ensure that we get nowhere near 25 milliamps. And in practice, LEDs pulling 25 milliamps would be far too bright prototypically. Dropping the resistor limits the current and reduces the light intensity. Try experimenting with resistor values, starting with around 1K and reducing the value as required to get the appropriate light intensity. Remember, you can only see the lights of real carriages when the ambient light is low. However, I appreciate that many layouts are only used in, let's say, normal room lighting, and therefore you probably need to have a slightly higher than prototypical light intensity to see any lighting whatsoever. Let's look at N-scale coach lighting. It's not easy, but it is possible. And here's an example of how the PCB unit has been fitted into an N-scale coach. And here we have the connectors. In this case, just using phosphor bronze strips. And from the final image, you can see it works, and it works well on the track, but it is a very tight fit. Let's look at DCC coach lighting Stayalives. Once again, dirty track, dirty wheels, points, etc. can cause the lights to flicker. A simple Stayalives circuit can prevent flicker, and a simple Stayalives circuit is all that we need in this case, because we do not need the high power to maintain a loco motor. Once again, we're using an electrolytic capacitor, a diode, and a resistor. Remember that electrolytic capacitors are polarity sensitive. If you do connect them the wrong way around, not only will it be ineffective, but you might find that you end up with the same sort of special effects that are so popular with some of our members: lots of smoke, lots of noise, and in this case, lots of unpleasant chemicals leaking out. Here's a Stayalives circuit fitted. On the left, this is the installation in the exhibition coach. As you can see, it fits quite neatly into the end vestibule. On the right-hand side, we can see the exact same Stayalive capacitor, resistor, diode fitted in a test coach installation. And this is to demonstrate the benefits of Stayalives. First of all, let's have a quick look at how we connect the Stayalive. In the case of the Stripboard DCC to DC converter, we need to take the connection across the electrolytic capacitor, bearing in mind that the positive is marked on the capacitor by the stripe. You can see red to the stripe side, black to the negative side. In this case, the converter is fitted with a 3.3 volt regulator to support the PMP19 kit. The image below shows the PCB version of the coach lighting kit. And once again, the connections from the Stayalive go across the electrolytic capacitor. Now let's look at the effectiveness of this on the test coach. Quite a dirty piece of track. The LEDs are flashing as you'd expect them to. Not a very attractive scene. Now I'm switching in the Stayalive. immediately it's flicker free. And what's more, if I lift the coach off the track, you can see how effective that simple Stayalive is in keeping the lights flicker free. Some considerations. Installation requires a reasonable degree of modeling competence. The PCB version requires SMD soldering ability and specific equipment, such as a temperature-controlled soldering iron, a fine tip, good magnification, but more specifically, practice, which I would certainly encourage. To complete the coach lighting, you might wish to add a tail lamp to the end coach. In this case, it's a period coach, so I'm using a 2mm red LED of the lighthouse or top hat style, plus a 10K drop-in resistor. For a modern coach, you could add a flashing LED. There are two ways that the LED can be connected, and that is either to the coach lights or across the PMP19 electrolytic capacitor if the lamp is required to remain on when the coach lights go off. I hope that you've all found something useful in this presentation, and I'd like to thank you for your attention, and I'll now stop sharing and try and answer any questions that you have. Thanks.